G'day, welcome to our second lesson into our reaction kinetics unit. In today's lesson entitled Temperature, Reaction Rates and the Boltzmann Distribution, we are looking at the lesson objective of describing the effect of temperature on reaction rates and illustrating this on what is known as a Boltzmann distribution. Learning outcomes we are addressing just below there. So we introduced this unit in the previous video, looking at the idea that reaction rates is a measurement of how quickly a reaction occurs, essentially. It's just the change in the amount of reactants against time. And we looked at the effect that concentration had increasing or decreasing will have on the rate of the chemical reaction. In this video, we are looking at how temperature affects reaction rates, and then in the next video, we're finishing off by looking at how catalysts affect reaction rates. So we talked about this idea of collision theory, the idea that particles are essentially just bumping into each other. They're just colliding, and if you have a successful collision, you have a chemical reaction. If you have an unsuccessful collision, reactants will just bounce off unchanged. And we looked at how that can occur. Let's look at how temperature affects this. So what does increasing the temperature do to the reactants? Well, firstly, let's just consider really what temperature really is. When you're talking about the temperature of the system, you're really just talking about the kinetic energy of the particles. So if you've got particles in a system with high kinetic energy, you're going to have a high temperature. If you have particles in a system with low kinetic energy, you're going to have a low temperature. So if you're increasing the temperature, that's essentially just increasing the kinetic energy of the particles. So increasing the temperature will increase the frequency of the collisions, because if they have a higher kinetic energy, they're moving more rapidly, they're going to bump into each other more often, and it's going to increase the energy that those particles collide with. So you imagine your particles moving around with a certain temperature, they bump into each other every now and then. If you increase how quickly they are moving, then the probability of them bumping into each other is going to be higher. It's going to increase the frequency of collision. And similarly, if they're moving faster, they're going to collide with a higher energy, aren't they? Therefore, there will be a greater chance of a successful reaction. Consider, are all particles in a system at the exact same temperature? When you leave say a glass of water out, why does it evaporate even though it is below the boiling point? If we think about the water situation, we know that water will have a boiling point at 100 degrees Celsius. So we can expect to enter the gaseous form at 100 degrees Celsius. But if you leave a glass of water in a room that is under 100 degrees Celsius, you can still get evaporation occurring. And that is because all the particles are in fact not at the exact same kinetic energy. So we can have things that evaporate below its boiling point because we could have, say, the particles on the surface with a higher kinetic energy than the particles at the bottom. So not every particle in the system will have the same kinetic energy. So when we do measure the temperature of a system, we are just measuring the average kinetic energy of that system. So let's consider if we have some sort of system, could be a glass of water, could be anything. Closed system, let's say it's in the liquid form. So we have the liquid conforming to the volume and shape of the container. So we have some particles that are moving with a high kinetic energy. We have some particles that are moving with a low kinetic energy. Some particles that are moving with such and such kinetic energy. The ones at the surface might be having a very high kinetic energy where they're even entering the gaseous form even though the system is below the temperature of the boiling point. So when you put a thermometer in, this is my thermometer, you get all the particles colliding with that thermometer essentially, and you get a reading on a thermometer of a certain temperature. You get X degrees Celsius. So all this temperature is doing is it's just getting an average of just even a small sample of the liquid that you're putting it in, the liquid in this situation, of the particles that are colliding and transferring its chemical energy, which is causing the thermometer to have a certain reading. So you're just getting an average kinetic energy of a sample of the particles in the system. And that's what we're talking about when we're talking about temperature. It's just this idea of an average of the kinetic energy. So within a system, not all the particles are at the same temperature. Not all the particles have the same kinetic energy. Sort of a long way to go about saying that. We can show all the energies of the particles in a system in something that is called a Boltzmann distribution. So some particles will have a very large amount of energy, some will have a very small amount of energy, the rest will be somewhere in the between of these two. You can graph this using a Boltzmann distribution named after Austrian physicist philosopher Ludwig Boltzmann, We like to name drop and give credit where credit's due. So Ludwig Boltzmann came up with the Boltzmann distribution. Smart cookie along with all the other names that we've looked at. All right, so it looks like this, right? We have the energy of the particles on the x-axis, and we have the number of particles up here on the y-axis. So we could see how many particles in a given system will have a certain amount of energy. So I could read it off there, read off my graph. Up at the y-axis, I would have that many particles with that much energy. I would have that many particles with that much energy, just how you read a regular graph. So by that, it means that the total area under the curve is the total number of particles in the system. So if we get the area of all of this under the entire curve, that is all the particles that is in my system. But we've been talking about chemical reactions, and we've introduced in previous units and discussed in this unit as well the idea of activation energy. So this is the idea that there needs to be a certain amount of energy that reactants need to have in order for the collision to be successful. If they collide with less than that energy, they'll just bounce off and we'll have an unsuccessful collision. So we can see a activation energy on a Boltzmann distribution. So this is just some arbitrary value for the activation energy. But what it's saying is that if these are all our reactants, the whole area under the curve is our reactants, the energy for the reaction to occur, the activation energy is here. So the particles with energy that is greater than that can have a successful collision. The particles with energy less than that cannot have a successful collision. So if the total area under the curve is all of the particles in the system, the area under the curve that is past the activation energy will show the proportion of particles that have sufficient energy to cause a chemical reaction when they collide. So all of the particles under here will have sufficient energy in order to have a successful collision, and all the particles below there will not. Rightio, so why don't you pause now and have a think about this. We have a question. If this is a Boltzmann distribution for a particular system at one particular temperature, what do you predict a Boltzmann distribution would look like if you were to decrease and increase the temperature? So draw a Boltzmann distribution showing an activation energy, just totally arbitrary, anywhere, just a thing like I've shown here. Somewhere on the graph, and on the same graph, draw a Boltzmann distribution to predict the effect of decreasing temperature and predict the effect of increasing temperature. If you're playing along at home, pause and have a go, have a think about that, and check now. So that's why we're here, isn't it? We're seeing what effects the temperature will have on a chemical reaction. So if we can see on a Boltzmann distribution the energy that the particles will have, we can see how temperature is going to change that Boltzmann distribution. So let's just think again. What happens when you increase the energy of a system? The average temperature will increase. The particles will move faster. They have a higher kinetic energy. We'll get more frequent and higher energy collisions, and therefore we'll end up with more particles that have an energy greater than the activation energy. So let's see how this will affect the Boltzmann distribution. So I got three Boltzmann distributions here. Let's say I had my initial temperature of my reaction being this green Boltzmann distribution. If I were to increase the temperature of that chemical reaction, we would see that a proportion of the particles will have more energy than they had before. So if I were to increase the temperature of the system, my Boltzmann distribution would sort of flatten out and the peak would shift to the right, and we would end up with a curve like that. If I were to decrease the energy, decrease the temperature of the system, then the particles would get less energy. So we would see the peak move to the left and the curve would, what's the opposite of flatten? It would sort of grow, wouldn't it? So this red one would be if the temperature was decreased. Given that this is the exact same reaction system, so this is my system done under one temperature, the exact same done under lower temperature, and the exact same done under a higher temperature, the area under all three of the graphs will be identical. Why? Well, if you think about it, we said just before that the area under the graph is the total amount of particles in the system. So given that this is a closed system, if we increase or decrease the temperature, we're not changing the amount of particles in there, are we? That's staying the same. What we're changing is the kinetic energy that those particles have. So all three of these graphs, the red, the green, and the blue, if you were to get the area under the graph, it would be the same in all three instances. And that's because the total number of particles has not changed. However, the relationship between reaction rate and temperature isn't explained by an increase in the frequency of collisions alone. So it's not just the fact that we're having more frequent collisions. Another factor affecting the relationship between temperature and reaction rate is to do with this proportion of particles that have an energy greater than an activation energy as the temperature is increased. So if I pop a random activation energy for this reaction, again, totally arbitrary, for my reaction, I need that much energy in order for a successful collision to occur. Let's see what happens to the proportion of particles that have an energy greater than an activation energy. If we look at my initial reaction, which was the green one, if I get the area under the green curve, in fact, it might be better if I draw this out so I can shade some areas. So I have a Boltzmann distribution. Good practice to draw these Boltzmann distributions so you become familiar with them. I have a y-axis and I have an x-axis. We said on the y-axis we have the number of particles. That's my little shorthand for number. Oh, let me try that again. We have the number of particles, and down here we have the energy of the particles. So I have a given chemical reaction that has a Boltzmann distribution like something like that. If I were to increase the temperature, then my Boltzmann distribution, the peak would move to the right and the curve would flatten out, so I'd get something like that, let's say. Now, the area under these two graphs, if I drew this perfectly, would be identical. So I said there was some sort of activation energy, let's say there. I might even increase my x-axis there. So that flattens out and that flattens out. So my activation energy is this point here. And we said the area, well, nice straight line, Connor. Let's see if we can fix that up a little bit better. Cool, nailed it. So the activation energy, we said the area under the graph is the number of particles, and the particles with energy greater than activation energy for my initial reaction, which was the black one, would be that area. However, you can see that when we increase the temperature, we significantly increase the proportion of particles that have an energy greater than the activation energy. So when I increase the temperature, my Boltzmann distribution now shows all of this having the particles greater than the particles energy greater than the activation energy. So we see a significant increase. Let's say if I were to decrease the temperature, so I get a higher peak that moves to the left, and we'll get something like that. We can see here that it's only this little bit there, which is significantly a significantly lower proportion than both the black curve and the red curve. So to put that in a very succinct sentence, as temperature increases, the proportion of particles with energy that is greater than activation energy that can have a successful collision will increase significantly. And we can see that by the area under each curve. So let's look at this really good diagram as opposed to my scribbles on the whiteboard. If we look at the red one, which is the lowest temperature, we have a small area. If we increase the temperature to the green one, you can see how significantly we have increased that proportion of particles. And then if we look at the blue one where we've increased the temperature again, we've increased that area significantly again. So let's just recap everything. Temperature and reaction rate. The Boltzmann distribution is a graph that represents the distribution of energies that a sample of particles will have at a given temperature. The area underneath the curve is the total number of particles. Changing the temperature will change the rate of reaction and consequently the shape of the Boltzmann distribution as we saw here. Your turn to have some questions. Pause if you're playing along and see if you can answer these. Question 1, describe what happens to the shape of the Boltzmann distribution as temperature increases. And then 2, suggest why increasing the temperature of a reaction by 10 degrees Celsius could double the rate of reaction. Pause and then check your answers against mine. So you could say something like this. For the shape of the Boltzmann distribution, as temperature increases, the distribution of molecular energies will change, causing the curve to flatten and the peak to appear further to the right. So that's what we see here. Red is the lowest temperature, then green, then blue. Curves flattening each time, the peak is moving towards the right. And then why increasing the temperature by 10 degrees could double the rate of reaction. Increasing the temperature will increase both the frequency of collisions and chance of successful collisions. Due to the distribution of molecular energies as seen on a Boltzmann, increasing the temperatures by 10 degrees Celsius will lead to a much larger proportion of particles with energy greater than activation energy, potentially doubling the rate of reaction. And with that, we finish our lesson on temperature, reaction rates, and the Boltzmann distribution. What have we done? We've explained and used the term activation energy, including reference to the Boltzmann distribution, and explained qualitatively in terms both of the Boltzmann distribution and of collision frequency, the effect of temperature change on the rate of reaction. Our task for this lesson, if you want to consolidate your understandings, pause, work through the table, one column at a time from the bottom to the top. Thank you for your time again. I will see you on the next video as we finish off this unit by looking at catalysts and reaction rates. Have a great day.